Hello friends, now we will discuss the configurations of BJT. First I will be talking about common base configuration. There are basically three configurations in BJT: common base configuration, common emitter configuration and common collector configuration. First I will be starting with the common base configuration. In common base configuration, the base terminal of the BJT is connected to ground. Input is given from the emitter terminal and output is taken from the collector terminal. So load resistance is connected in the collector. I will be considering collector base junction with reverse biasing and emitter junction with forward biasing. This is the circuit diagram I will be considering here. In common base configuration, we will be talking about NPN transistor here. That is, if arrow is coming from emitter outward from emitter, so that is NPN transistor. So in common base configuration, I will be talking about two types of characteristics. First is called input characteristic and second I will be talking about output characteristic. So let us talk about the input characteristic first. Input characteristic of common base configuration. The input characteristic of common base configuration is defined by, that is, the current, that is the voltage VBE, that is this voltage is function of, that is function of the voltage, the input current IE and the output voltage VCB, not output, rather the collector junction voltage, that is VCB. This is the function which will be defining the input characteristic of BJT. If you draw the characteristic here, that characteristic is like this. X-axis I will be taking VBE, that is your base to emitter junction voltage. Y-axis I will be taking, that is emitter current. Although in some books, in Millman Healthcare especially, these are reversed because this is y-axis, this is x-axis, that is how they have taken. But in most of the books, x-axis or in simple PN junction, we take voltage on x-axis, current on y-axis. That is why I have taken like this. But as far as mathematical convention is concerned, y-axis is always this, left hand side is y-axis, this is x-axis. Otherwise you will find a reversed notations in Millman Healthcare. Fine. So if you see the variation, when you have input junction here, it is forward biased. Why? Because it is negative, it is positive. So input junction means emitter junction is forward biased. So initially there is no current in the emitter terminal, but when you go on increasing the forward biasing voltage, after that it starts increasing like this. This is how, this is basically the simple characteristic of a forward biased PN junction. This is your cut-in voltage. Fine. And this characteristic is dependent on one thing, that is VCB. Please do remember that. This is function of VCB. If you go on increasing VCB, you will find this characteristic will shift like this. This will be shifting. How it is happening, why it is happening, we will see that later. So I will be saying, say it is for VCB1, it is for VCB2, it is for VCB3, like this. For the same base to emitter voltage, I have the different values of emitter current. You can see please. For same base to emitter, I have different values. VCB3 is more than VCB2 is more than VCB1. So when you can see, when base to emitter voltage is kept constant but collector junction voltage is increased. So when collector junction voltage is increased, you will find the characteristic shift towards IE axis, towards the vertical axis, towards the current axis. Characteristic is shifting this way when VCB increases. What is the reason? Let us try to find out the reason. In base region, please try to understand the region of change in ammeter voltage, ammeter current with VCB. Please try to understand the concept. This is your BJT, this is base terminal, this is ammeter terminal, this is collector terminal, this is VCB voltage. Fine. When VCB is positive, so this is junction, collector junction, this is ammeter junction. At collector, if you talk about the depletion layer at collector junction is very narrow because it is forward biased, but depletion layer at collector junction will be little wide as compared to the ammeter junction because it is reverse biased. Fine. So when you increase the voltage VCB, that is reverse biasing voltage at the collector junction, the depletion layer width will increase. Why? If you remember, width of the depletion layer is directly proportional to V naught plus VCB power 1 by 2. The width of depletion layer is directly proportional to root of reverse biasing voltage. This is what we have seen in case of PN junction diode. When a PN junction diode is reverse biased, the width of depletion layer increases with increase in reverse biasing voltage. So same should apply here. This junction is reverse biased, collector junction is reverse biased because of this voltage. This is reverse biasing supply voltage, but the effective voltage is this. So when you increase reverse biasing voltage VCB, this width of the depletion layer will not remain same, rather it will increase like this. I hope the concept is clear. Width of the depletion layer at collector junction will increase. What will be the effect? Initially, say this is N, this is P, collector is P type, this is N type. So when ammeter junction is forward biased, the carriers will be injected electrons. Carriers means majority carriers in ammeter, but now these becomes minority carriers in base. When you inject the electrons, their concentration decreases, and at the edge of the depletion layer it becomes 0 earlier. Now when you increase VCB, at the edge of the junction it becomes 0. Please understand what has happened. This edge of the depletion layer has shifted here, and concentration at the edge becomes 0 as it reduces to 0. The gradient of minority carrier concentration in the base region is increasing, and if you remember, the ammeter current IE is equal to Q dP then dP by dx multiplied by area of the ammeter junction. This is not D, this is dN. This is dN. Why? Because I am talking about the injected electrons in the base. Base is P type, so injected electrons is nothing but N. So these are nothing but current of ammeter component which is being entering here. This current is ammeter current which is becoming diffusion current in the base region, and that is given by A is area of ammeter junction, Q is charge, Dn is diffusion constant of electrons in base, minority carriers, electrons are minority carriers in base, and this is the gradient. When you shift this 0 with increase in VCB towards this side, when the width of the depletion layer is increasing, this gradient is increasing, this gradient is increasing, and when gradient is increasing, your ammeter current will increase. I hope concept is clear. I am just repeating for your understanding again. Initially at certain voltage, the depletion layer is here. So minority carriers which are electrons in the base region will be maximum at ammeter junction, which are being ejected, and reduces to 0 at the edge of the depletion layer. When you increase the reverse biasing voltage at collector junction, that edge of the depletion layer shifts inward. Why? Because width of the depletion layer increases. So that 0 which was earlier here now it is shifted here. So gradient of minority carriers in the base region is increasing, slope is increasing. Because of change in gradient, the current which is being injected into the base region is increasing, and that current is what? That is emitter current because of electrons. And if emitter current is increasing, that is how the characteristics are shifting. This effect of change in width of the base region with change in the reverse biasing at the collector junction is called base width modulation. Is called base width modulation. If reduction in effective width of the base region, suppose earlier if width was W and now it has reduced to W dash, this decrease in effective width of the base with the increase in reverse biasing voltage at the collector junction is known as base width modulation. That is, base width modulation is also called early effect. So the input characteristic curve shifts towards the current axis with increase in VCB because of the early effect or base width modulation. I hope the concept is clear. Fine. I will be discussing this topic again, that is your early effect, but for the time being just remember it is because of the early effect due to which characteristics are shifting. Fine. So this is your input characteristic. This is important part to be understood, important part to be remembered. Fine. Now this cut-in voltage, remember cut-in voltage in input characteristic is of order of 0.1 volt for germanium and about 0.5 volt for silicon. Cut-in voltage is of 0.1 volt and order of 0.5 volt for silicon. Please do remember the figure. Fine. So this is your input characteristic. The second characteristic of common base configuration is called output characteristic. The output characteristic is defined as the output current which is the function of that is again the input current IE and output voltage VC. This relationship defines the output characteristic. So let us see the output characteristic of common base configuration. Here again I will be taking since this current is y-axis, so here I will be taking the current on y-axis as per the convention of mathematics. So this axis will be your input axis, this axis will be your output axis. So this is IC and I will be taking VCB on x-axis. Fine. And if you remember, one by one I will be talking about these relationships. This IC is function of emitter current. So that is rather than writing the relation, just remember, just recall that is IC alpha IE plus IC naught. That is the relationship between IC and alpha. But remember, this relationship is applicable when your BJT behaves like an amplifier. Now I'll see that, we will discuss that. So when IE is 0, when this current is 0, IC is equal to IC naught. So current is very small, this collector current is very small, that is equal to IC naught when IE is 0. When input is 0, the current is equal to IC naught. Remember, IC naught is what? Reverse saturation current in collector junction, and reverse saturation current is of order of microamperes for germanium and in the range of nanoamperes for silicon. So that current, and normal current is in the range of milliamperes. Normal collector current is in the range of milliamperes. But when emitter current is reduced to 0, your collector current is becoming in the range of microamperes or nanoamperes. Microamperes for germanium and nanoamperes for silicon. That current is negligible. So I will say your load current is reducing to 0 when input current is 0. That is what I wanted to say. So this current is negligible. Later on, when you apply certain value of, I'll show it like this, then like this, then like this, and so on. So when you increase ammeter current and further like this, so this is IE1, this is IE2, which is definitely more than IE1, this is IE3 more than IE2, this is IE4 more than IE3. So when you go on increasing the ammeter current, the collector current is increasing, and that increase is because of this relationship. IC is proportional to IE, but with certain offset value, that is IC naught. So current is increasing with increasing ammeter current. Which current? Collector current, your output current. So I am controlling the output current with the input current. Since output current of BJT is being controlled by input current, because of that we call BJT as current controlled device. So BJT is what? BJT is a current controlled device. It can be used as a current controlled source, current controlled current source. Please do remember, this is important point to be remembered here. Fine. So now there is more thing to learn. Let us see that these characteristics will be falling like this, and that is very narrow, like this, in this region. This is VCB equal to 0. So to the left, when VCB is slightly negative, VCB is slightly negative across the junction. So we will see one by one. VCB becomes negative means forward biased. VCB negative means, VCB positive means forward biased. I'm sorry, when VCB positive means reverse biased. When VCB becomes positive means this plus this minus, it becomes forward biased. We will talk about it later. This region where IC is equal to IC naught, this region, very narrow region, current is of order of microamperes or nanoamperes. This region of output characteristic is called cutoff region. When your ammeter current is 0, there is a condition here. When ammeter current is 0 means input current is 0, the output current is of order of nanoamperes or microamperes, that is IC naught. That region of operation in output characteristic is called the cutoff region of BJT. In cutoff region of the output characteristic, or in cutoff region, the BJT behaves like an open switch. Why open switch? If you talk about this, if current is becoming 0, so it is behaving like open here. There is no current in the junction. The current in the junction is of order of microamperes, nanoamperes. So I am saying your BJT is behaving like an open switch in cutoff region. Fine. So please do remember this. Then let us talk about the second region where your ammeter current, your collector current is increasing linearly with ammeter current. This region is called active region. Remember, when the collector current increases linearly with the ammeter current, when output current increases linearly with the input current, that region of operation is called active region. And in active region, ammeter junction is forward biased, your collector junction is reverse biased. Whereas in cutoff region, IE is 0. If IE is 0, VCB is your reverse biased. In general, remember, in cutoff region we define both junctions are reverse biased. That is the definition of the cutoff region. Not only IE 0, you will say when both junctions are reverse biased, your ammeter current will also become 0. Fine. So that is cutoff region. In cutoff region, both ammeter and collector junctions are reverse biased. In active region, emitter junction, input junction is forward biased, collector junction, output side junction is reverse biased. Fine. Then I am left with this portion of the characteristic where VCB is negative. This region of operation from here to here, this is called saturation region. Remember, when your VCB is becoming negative, this region is called the saturation region. In saturation region, the voltage across the device is very small and current is increasing suddenly. So current is large, but voltage across the junction is small. So it is behaving like a switch, closed switch. In saturation region, VCB is negative means forward bias junction. So in saturation region, your emitter junction as well as collector junction, both are emitter junction and collector junction are forward biased in saturation region, number one. Number two, the voltage across the collector junction is very small and your collector current increases sharply depending upon the emitter current. So I will say in saturation region, your BJT behaves like a closed switch. So I am just summarizing. In cutoff region, both junctions are reverse biased. Input current is 0, output current is negligible, almost 0. BJT behaves like an open switch. Number 2. In active region, output current is directly proportional to input current. Emitter junction is forward biased. Collector junction is reverse biased. In that region, it behaves like an amplifier. BJT behaves like a current amplifier. Third point, in saturation region of operation, the voltage across the output junction is negligible, very small. Number 2, the current increases, collector current is large. Number 3, the BJT behaves like a closed switch. Number 4, emitter and collector junction both are forward biased. Please remember all the points whatever I am saying. You have plenty of questions from whatever I said. If you have pen and copy, please do write it down on your copy, just for your revision purpose in future. Otherwise you may have to see my video again and again if you are totally dependent on video. Fine. So these are few points. This is your output characteristic of common base configuration. There is one more characteristic here. If you go on increasing VCB, here, that is your collector voltage, after certain point of time, what will happen? There will be breakdown. At the collector junction. Why? Because of the reverse biasing voltage. When you go on increasing reverse biasing voltage at the PN junction, after certain point there is avalanche multiplication, breakdown of the junction. This region is breakdown region, and remember, diode, your PN junction, your BJT is never operated in breakdown region. Beyond this, it is breakdown region. Fine. So, but it is not operated in breakdown region of operation. So this is all about output characteristic of BJT. So I will again come back to what I discussed earlier, that was the base width modulation or earlier effect. So let us see what is earlier effect. Although I have given you the complete explanation of earlier effect, just a review of that and some more points I will be adding to whatever I discuss. So this is your BJT. I will be drawing little bigger diagram so that your visualization is clear. This is your collector junction, this is your emitter junction, this is your collector junction, this is emitter terminal, this is your collector terminal, this is your base terminal. This voltage is, your emitter junction is normally forward bias, so VBE, rather than drawing that circuit, I will be just mentioning this is VCB. Your collector base junction, that is collector junction, is Sometimes you call collector base junction, sometimes you call collector junction, that is same thing. Fine. So in normal case, I have very small depletion layer width at this region. Fine. I have larger depletion layer width. I am not drawing the depletion layer width here, but it is there as well, like this. Fine. Both sides of the junction, like this. Fine. So I am not changing VBE here. I will see the effect on operation of BJT when I change the reverse biasing voltage, because that was the controlling voltage in input characteristic of BJT. If you remember, what IE is equal to function of VCB, and that was VBE, your input characteristics VBE, not VBE, that is yes, VBE, and ammeter current. If you talk about this, ammeter current was function of, yes, voltage VBE. VBE was function of current IE, and VCB. I'm sorry, that is what we discussed earlier. Now let us see here what I told earlier. This is NP, and I'm talking about NPN transistor. When it is NPN transistor, so electrons from since your emitter junction is forward biased because of this voltage, electrons will be injected, and the concentration of electrons is very high. When these are injected into base, their concentration is 0 at the edge of the junction, at the edge of the depletion layer. When you increase the voltage, your edge may be shifting towards left. Your edge will be shifting. So edge is shifting, edge of depletion layer is shifting this way. So when your edge is shifting, remember the concentration of minority, here electrons which were injected from emitter to base region are minority carriers, and their concentration decreases like this and becomes 0 at the edge of the depletion layer. When you are shifting edge this way, this remains same. Why? Because I am not changing VB, but here it will edge is shifting, so concentration will become 0 at this point. So if you talk about the width of the base, say earlier it was WB, now the width has reduced to WB dash. Effective width has reduced. So this shifting of edge of the depletion layer deeper in the base region towards left is resulting into decrease in the base width. If effective base width is decreasing, what will be happening? Let us see. The carriers which were being ejected from this to this will be, suppose 100 electrons are injected from here. Earlier it was 99. Now I'll say there will be less possibility of recombination in the base region. Why less possibility? Because width is already narrow. Width of the base region is kept less than the diffusion length. If width is already narrow, so the possibility of recombination of the minority carriers which are being ejected in the base region will be less, and more carriers will be reaching, because once the carrier enter into the depletion layer, I am assuming there is no recombination. Recombination occurs only in the neutral region. Once it is entering into the depletion layer, there is no recombination. That is our assumption. So if effective width is reducing, there will be less probability of recombination of minority carriers in the base. More and more carriers will be going towards the collector side. So the component of collector current will be more here. So if you talk about the collector current component I and C1, because of these electrons which are going from here to here, this will be alpha into what? I and E. Component of current I and E we have just seen earlier. Fine. So if less number of carriers are recombining, so alpha is increasing, Why? Because more and more carriers are reaching this site. So what I mean to say is the collector current is increasing. Collector current is increasing. Why collector current is increasing? Because the gradient is increasing. Collector current is increasing. Why gradient? Please do remember, my collector current is function of alpha and IE. 2. Alpha is nothing but, that is basically the fraction of carriers which were injected from emitter side which is reaching there. That is alpha. Fraction of carriers means current, you can say. The current which was injected here, the fraction of that current at collector. You can say that way also. Here I and E is also increasing. Why? Because I told earlier I and E is what? That is approximately equal to emitter current, which is the area of emitter junction, Q dn, that is diffusion constant of electrons in the base region, into dn by dx. This dn by dx is gradient of minority carriers in the base region. When this depletion layer edge is shifting towards this side because of increase in VCB, when VCB is increasing, it is shifting this way, the gradient is increasing. And if this gradient is increasing, emitter current is increasing. If emitter current is increasing, your collector current is increasing. Number 1. Number 2. If more and more carriers are reaching here, so fraction of carriers reaching at the collector junction is increasing, therefore alpha is increasing. So 2 observations. If you talk about the effect, this reduction in base width because of increase in voltage VCB at the collector junction is known as base width modulation. Please do remember this. This is important point. You have a lot of questions on this. Base width modulation is also known as early effect, EARLY, early effect. Fine. Now, this is early, not earlier. This is early effect. I'm sorry. This is early effect, not earlier. Early effect. Now, so what are the effects? Alpha is increasing, INE is increasing, INC is increasing, and you know what is beta? Beta is alpha upon 1 minus alpha. If alpha is increasing, this is increasing, this is decreasing. If this is decreasing, this will increase. So beta is also increasing. So effects of early effect, or you can say consequences. पहला क्या था? Alpha is increasing. दूसरा beta is increasing. तीसरा your IE is increasing. Why IE? Because IN is increasing. That is one component of the emitter current. Fourth, IC is increasing. Fine. Then what has happened? Your base current is decreasing. Why it is decreasing? Please see. If the number of carriers recombining in the base region are reduced because of the reduction in base width, so what is happening? Your IB is reducing. Then what if next effect? Your base width is decreasing. These are some of the points to be observed, and remember, these are effects of the base width. Do remember all the points, because these are potential objective type question in engineering services and 1 mark question in GATE. I hope the concept of early effect, concept of base width modulation, the input characteristic, output characteristic of common base configuration is clear. If you have any doubt, please do see the video again and again, because you will understand every thing once you see video maybe twice or thrice. So this is important topic as far as exam is concerned. You can have question from that. Thank you for watching, and again I'll request, please do subscribe the channel if you are liking it. Please do share it with your friends, because it will benefit, it will definitely give advantage to your friends as well. Please do share, do subscribe the channel. Thank you very much for watching the video.